All right. Hey, everybody. So yesterday we were talking about NumPy, and we talked about we did few tasks on our NumPy lab. We talked about the memory, and we talked about the vectorized operations. We talked about how the fancy indexing, basic indexing works in NumPy, and we talked about the strides, a little bit about strides also, and the reshaping, how the views happen in NumPy. And we talked to a high level view took a high level view of machine learning. And today we are first topic that we are going to cover is broadcasting. And broadcasting, yesterday the question was asked by Lohit that, okay, if we have a NumPy array or a vector, 1, 2, 3, 4, and if we are adding 5, then what happens that in one go itself, I will be able to add 5 to each and every element. So 6 and 7 and then 8, then 4, depending upon how many parallel operation capability I have in my system. That those are called SIMD operations. So we'll be able to, and Lohit had asked, oh, that if it is 5, then how does it happen? Does it create a copy like this under the hood, a vector and then parallel 4 operations? But we learned that it doesn't create a copy. NumPy doesn't create a copy, but it has broadcasted 5 across 4 elements. All right. Think of it like broadcasting from Delhi to any place in India for Delhi Doordarshan. All right. So it broadcasts the data. So this was a prime example of broadcasting when we have a vector and a scalar. All right. Now we'll come to another. Broadcasting doesn't happen only in the vector and the scalar, right? The broadcasting can happen in if we have a vector and a vector. And vector and a vector also. All right. We can do the arithmetic operations which are done in NumPy. The vectorized arithmetic operations which are getting done using the help of broadcasting. So if we have a vector and vector. So the methodology right now for broadcasting is that there are certain rules of broadcast. I'm not going to tell you about the rules. We will develop those rules with our common sense. In AIML, we'll start developing our mindset for AIML that, okay, is this common sense? Is this not common sense? And from that common sense, we will be able to drive the rules. If we have a vector and vector, if we have a vector 1, 2, 3, and I have a vector that is 5, 6, 7, and let's call it A, let's call it B. If I do A plus B, what will be the result? I will be able to do 5 plus 1, 6, 8, and 10. Makes sense? I will be able to do the things. If I have just one element, we have already seen it. If we have a broadcasting of a vector and a vector, 1, 2, 3, 5, 6, 7, 8. If I add this, A plus B, what will be the result? Let's see the shape. The shape of this is 3. Shape of this is 4. Now the system doesn't know how to stretch the data. How should I stretch the data so that I am able to add? Because I have to consistently stretch the data. So then, if I do this, then that should be giving us a broadcasting error. Basically, the system is saying, I don't know how to stretch the data so that I can add 3 elements and 4 elements over it. So let's try it in the lab that we had and try to do the broadcasting over there. Pairwise distances. Okay. We'll reset it and go. All right. We'll have A is equal to np.array np.array of 1, 2, 3 and a B np.array of 4, 5, 6. All right. 4, 5, 6. And we'll have C, which is equal to A plus B. And try to print C. If I try to print C, oops. If I try to print C, then I will be having 5, 7, 9. 4 plus 1, 5 plus 2, 3 plus 6. But if I have the shape mismatch, is there, let's call it 5, then I'll be getting a broadcasting error. And it will be saying operands cannot broadcast together with the shapes 4 and 3. Now the NumPy gets confused. All right, everybody cams, please. If your cam is not on, then I'll be requesting one more time. Neither I'll be removing it from the class. All right, the cams have to be on always. All right, I should not be saying it again and again. I lose my concentration. So this is vector broadcasting. Now, if we have vector and matrix, for example, if we have the data like a vector 1, 2, 3, and a matrix, let's take that matrix as 2, 3, 4, 5, 6, 7. What will happen in this scenario if I add both of them? Then the NumPy imagines this, that I am going to repeat this again one more time. I'm going to stretch the data. It doesn't create a copy. It doesn't actually make a new matrix. It just stretches the data like this. It imagines. It broadcasts the data like this. And then when we are adding it, we'll be able to add 1, 2, 3 right here also. We'll be able to add 1, 2, 3 right here. Make sense? So 2, 3, 4, 1, 2, 3 is added. We'll be having 3, 5, 7, and over here 6, 8, 10. This should be the result that I should be getting. So broadcasting is happening like this. Let's try to write it down. If we have,
But why this will not fail in this case? Because this time also shape is different, right? It's 2
yeah,
comma 3 and then it's 3 comma.
because the NumPy is able to imagine that I have to broadcast it like this, right? The shape was different in 1, 2, 3, 5 also. All right, but it was able to broadcast it like this, right? So, but
Hmm.
it's not only the shape, it's the confusion that
Confusion that the
that NumPy is having, that okay, how to broadcast? Can I broadcast this? Can I broadcast this onto this? If I broadcast this onto this, then 4 is pending, no? Make sense? So there is an inconsistency. Does it make sense? But over here, if I do this, then I'll be able to broadcast it like this. Let's see it in action.
So what if there were 6 elements in the first
We'll see. We'll see.
vector?
Let's see the first one. Okay. So 1, 2, 3. Just focus on right now. We'll do the other scenarios also. 1, 2, 3, 4, 5, 6. Remember, this is the way that I can declare the matrix. It has to be nested. All right. And 4, 5, 6 over here. 1, 2, 3. Let's take 1, 2, 3 on. Or 2, 3, 4. 1, 2, 3. And let me remove. All right.
Is this same
One,
as matrix multiplication rule?
just a moment. Let's see this first. Okay. 2, 3, 4. All right. And 1, 2, 3. If I do A plus B, if I print C, then I should be at 3, 5, 7, 6, 8, 10. All right. This is the way that the broadcasting is happening. Imagine that this is being broadcasted like this. It is totally different from the matrix multiplication rule. Make sense? It's just broadcasting the data, a vector onto a matrix. How? That we are broadcasting the vector like this so that it can be added like this. So NumPy understands that the user is, what he's trying to do is he's trying to add 1, 2, 3 to this, 1, 2, 3 to this. All right. So you do not need to reshape. The advantage of broadcasting is without reshaping your data, you are able to do the arithmetic operations. That's a crux. That's a logic of broadcasting. Make sense? So that I am able to in- implement the arithmetic operations without reshaping the data structure. All right? Because if we are reshaping the data structure, it takes compute. NumPy wants to do the things very, very fast. All right? If we have this right here, will I be able to do the things? Will I be able to broadcast? All right. If some user is providing the data like this, what he intends to do, what does he want to do? Can you
Add
think?
one to every element.
Add one to
Add one
add,
to every.
add one to each and every element. So he wants to do two,
Yes.
three, four, five. Basically, this is what he wants to do.
Yeah.
And NumPy is able to imagine that yes, this is what the user is trying to do. So what does it that NumPy does? It basically broadcasts the data towards this side. Imagine it broadcasts like this and broadcasts like this. And it will
Then
be able
again,
to.
I have a question. So in the first case, in the word 1D array, 1D
Uh-huh,
like a vector, right?
uh-huh.
So if the one A was 1, 2, 3, and the B would have been 1,
Okay.
then also it would have like imagine like, okay, fine, it's supposed to add element like now 1, 2, 3 is 3 comma, shape is 3 comma, right? For
Yes.
B, say it is 1 comma. In that case also it will throw error or it will broadcast
Where?
for
Right here?
vector. Yeah, so 3 comma and this is 1 comma.
This is not one comma. This is one, the scalar.
No, no, like this is in like a list. B equal
This
to list. Yeah.
B is equal to one, right?
No,
Yeah,
B
this is one.
equal to and in bracket. Yeah.
Yeah, this is one comma, right? This is a vector,
Yeah.
matrix and a vector.
No, in the second case, say I have vector and vector. The first vector is 1, 2, 3, so 3 comma. And
Okay,
then second one is a 1. Yeah, so 1 comma. Now what will happen in this case? It will still broadcast.
we'll see. We'll see. All right. This is three. This is one. All right. Should it
Yeah.
broadcast?
Yeah, it should, right?
Let's see it. All right. If we, okay, I'll come to your question. Can I complete this one first? All right. So if we have just one, then A plus B should be giving me C, which is equal to 3, 4, 5, 5, 6, 7. All right. 3, 4, 5. Just double to 5, 6, 7. Yeah, 5, 6, 7. This is 4, 5, 6 now. This is 4, 5, 6. So this should be 5, 6, 7. All right. So it broadcasted the data like this. It broadcasted the data like this also. Make sense? So this is in case of matrix and a vector. If we have a vector and a vector, let's see that. That is A, D is equal to NP array. NP array 1. Did I delete A? Okay. D is equal to NP dot array of 1, 2, 3. 1, 2, 3, 4. Okay. So ideally, if we are doing this, 2, 3, 4, and just one over here, a vector. Make sense? If I'm trying to do this, then what the user intends to do is add one to each and everything, right? So we should be having 3, 4, 5. Since the dimension is one, it is able to broadcast it. That this one will be broadcasted across, just like we were able to do it right here. Make sense? So if it is working right here, it surely should be working right here also. Make sense, Pooja? And your intuition is not incorrect at all. If we do this, then we will be having C is equal to prints D plus B. All right. And we'll be having 3, 4, 5. Make sense? So it did broadcast. Just the way that we imagined, it will broadcast right here. It will broadcast right here. All right. And this leads to one of the rules of broadcasting. Either the shapes should be matching. Either the shapes should be matching from the right. If we have to write the rules of broadcasting, the shapes of the data structure should be matching from the right. We start matching them from the right. Either they should be matching or one of them is one. One of them is one. There is a mismatch. But one of them is one, that's fine. Then I'll be able to broadcast. Then the system knows that it has to broadcast like this, right here. It has to broadcast like right here. Make sense?
You
And
mean shape one, right?
this will lead to the first broadcasting rule, that either the shapes are equal or the shape at that particular place where we are matching should be one. All right. Not the shape everywhere. The shape, it has to be just a vector. Shape should be one. Make sense? So in case if it is 1, 3, and 4, 1, if that broadcasting rule is correct, which we derived from here, from our common sense, even this will be fine. Make sense to us? This is upcoming. Let's not run over there yet. Okay?
Is it same for all the arithmetic operations like multiplication and everything?
Yeah, we will be able to broadcast plus minus multiplication. All right, whatever we are
So
doing, division.
if you have a 3, 3 matrix and 3 vector, how does the multiplication happen?
No, are you talking about the multiplication of the element-wise multiplication, or are you talking about the dot product? You are confusing the dot product or the cross product with the multiplication, element-wise multiplication.
So I have a 1, 2, 3 and 4, 5, 6 matrix
Uh-huh.
and a new vector 1, 2, 3.
Okay.
And how does the multiplication happen in that case?
What kind of multiplication? There are many kind of multiplications in the linear algebra. Is it element-wise multiplication? Is it the dot product? Is it the cross product that you are thinking?
So here we are giving A plus B, right? So if we give A into B, how does it happens?
It is element-wise multiplication. You are confusing it with the dot product. You are thinking that the matrix multiplication should be happening A, B, C, D. If I have E and F, G and H, then ideally the matrix multiplication should happen AB with EG and CD with G, EF, FH. Make sense? If you are imagining that, then you are going towards the dot product. That is not the element-wise multiplication that you have. Make sense, Sushil?
Yeah.
We'll come to that when we go to the linear algebra. All right.
Yeah.
For now, if you have to do the arithmetic operations, just keep yourself to the pure arithmetic operations only. Do not go to the linear algebra. Do not think about matrix multiplications. Do not
No,
think
I was
about
just confused like with the multiplication with the matrix and a vector. So I was.
Okay. Again, arithmetic operation of multiplication or the linear algebra uh, multiplication, that is the dot product or the cross product. Two different things altogether.
Yeah.
All right. So you need to firstly, we have to work on the linear algebra part, that, okay, what is the matrix multiplication? All right. Matrix multiplication and the arithmetic multiplication with a scalar or with a vector and a matrix are different things. All right.
Oh, yeah.
So Lohit, yes, go ahead. What's your question?
Yeah, I mean, like these two scenario got me thinking, like, then what's the shape of a scalar? Like, yeah,
If I
I'm good.
if you call shape dot shape on a scalar, what will happen? Will it be having a property of shape?
I don't think so because like we are not formatting it like a vector, like a 1D vector.
So the shapes are pertinent to vectors and the matrices only. Makes sense? So if it is a scalar, it is the simplest data structure. It is the simplest form of data type that we have. So I can broadcast the scalar as it is. Don't think about the shapes in case of scalar.
Okay.
Make sense? All right. Yes, Hemant, go ahead.
Yeah, Jaspinder, when you said the rules, I understood it when you said either one of them must be one or
Mhm.
it must be the exactly same shape. But I lost you when you said starting from the right, it must be the same. Did you mean the number of columns must be the same?
Let's go to the matrix here. All right. We are still at matrix and vectors. All right. We have not gone to matrix and matrix where we have this kind of shapes now. Let's go over
Okay.
there and then we can talk about that. Make sense? All right.
Sure.
Okay. Yes, Alok?
Uh, um, uh, what can be the real world example? Where are we using the broadcasting in machine learning or the deep learning? Where is
You
the
just
need
said.
of
Okay. For example, what happened right here when we did this? When we, uh, okay. If I have to subtract the mean from the x, if I have to subtract the mean of, uh, for example, in the further exercises. All right. So this is one of the ways that we will be standardizing or normalizing the data. That we will be, each and every entry inside the matrix will be for a feature. For example, if we took a mean, we took a standard deviation, we'll be subtracting the mean and we'll be dividing it by sigma. What is happening over here? This is a matrix. This is just a scalar. What is happening over here? Broadcasting. Make sense? Every arithmetic operation in the real world that you have to do on the on the data, whether it is vector, whether it is matrix, wherever you are doing the arithmetic operations, you are using broadcasting.
I was thinking, trying to relate it with the neural network, we add bias. So you're also using it broadcasting. I was trying
Yeah,
to relate it with that.
yeah. Any operation, any arithmetic operation where you are using, where you are doing the arithmetic operations, that you are using broadcasting. Okay.
Thank you.
All right. Let's go to the matrix. If I have 1, 2, 3, 4, 5, 6, and another matrix that is 7, 8, 9, and 10, 11, 12. Will I be able to do the arithmetic operations? And if the arithmetic operations happen, what should be the result?
8, 10,
8,
12,
10, 12.
12,
That is correct. 14,
14,
16,
16,
and 18.
18.
All right. So let's do that. So this is 3 by 3. Sorry, 2 by 3. This is 2 by 3. So if you see, the shapes match. All right. This matches with this. This matches with this. Cool. So and take print C over here. I need to have C as, I need to have B as a 1, 2, 3. 1, 2, 3, 4, 5, 6, and this one has 4, 5, 6, 7, 8, 9. Sorry. And this has 10, 11, 12. Okay. If I do this, then I should be able to 8, 9, 10, and 11, 12, 13. What happened? Oh, I'm doing this till this. A plus D. All right. So we are able to broadcast. Okay. Now, if we have this kind of situation, a matrix, not a vector. This is a matrix, okay? Then 2, 3, and this one is 1, 3. What is the user trying to say? If I'm doing this arithmetic operation, what is the user trying to do?
That add 7, 8, 9 to every row, like column by column.
Add 7, 8, 9 to every row. All right.
Yeah.
So if I add 8, 10, and 12, and over here, I should be having 11 and 13 and 15. So imagine the broadcasting is happening like this. All right. So we have 7, 8, 9 over here also, and then they are added. So if we do this, it works. Remember, the shapes don't match exactly. The shapes don't match. 3 matches with 3. But remember that one of them is 1. So by common sense, the broadcasting can happen like this. Make sense? So if I do this and I give it this as a 7, 8, 9, the broadcasting will be able to happen and it will be like this. More than broadcasting happening, we have to understand broadcasting giving us an error. All right. In what situations? If I do this, will the system be able to broadcast?
No, error.
We'll be adding an error. 2, 3, and 1, 4. 3 and 4 mismatch. Although this is 1, that is fine. The system doesn't know that I have 4 elements and I have 3 elements, 3 columns and 4 columns. What to do? How do I broadcast so that I am able to do the arithmetic operation? There, the NumPy should fail. So if I do this, if I add 10 over here, it should be throwing us a broadcasting error. All right. With 2, 3, and 1, 4, we will not be able to broadcast. All right. So with these, some exercises that we did, based upon that, let's try to draw the conclusions or draw the rules of the broadcasting. One, firstly, align the shapes to the right. This is especially handy when we are doing the matrix and the vector. Make sense? Then dimensions match. Dimensions match if they are equal or one of them is 1. Either they should be exactly matching or one of them should be 1. We just saw that, right? In the scenario where we had 2, 3 and 1, 3. We were able to do it. 3, 3 matches, they don't match, but one of them is 1. Make sense? So the third rule is the missing, especially in case of matrix and vector, the missing dimension are treated as 1. All right. So if this is not a matrix, if this is just this, it's a vector, not a matrix now. This is a matrix of 2 by 3, 2, 3 shape. And this is just a vector of 3. What does the system do? Remember, we were able to broadcast. Make sense? If I remove this, let's do it again. If I remove this as the matrix and 7, 8, 9 on, now we are broadcasting a matrix and a vector. And we were able to broadcast it like this. So what happened? As per the rules of broadcasting, we were able to do it. Basically, broadcasting did what? We had the shapes like this for the data structure. It moves all the dimensions to the right. Align all the shapes to the right. So it imagined 3 over here. This 3 was moved right here, and this missing dimension was imagined as well. And now, if I'm comparing it to 2, 3, 3, 3 match, 2, 1 don't match, but one of them is 1. And we were able to successfully broadcast the data. So these are the 3 rules of broadcasting. Align the dimensions to the right first. Then dimension should exactly match, or one of them should be equal. And the missing dimension can be imagined as, treated as 1.
Can you explain me when you say one of them is 1 with an example once
This
again?
one?
Yeah. It means one row, right?
Okay. We did this, right? If I go back, all right. Now, this is a matrix, correct? Matrix of 2, 3 and 1, 3, correct? If I print the shapes, okay, print A dot shape and print B dot shape. All right. What happened? Why is it not able to print? Oh, A
It's
dot
D
shape,
dot C.
D
It's
dot
not
shape.
B.
It's D dot shape. All right. So 2, 3 is the first shape. The second shape is 1, 3. Make sense? So 3, 3 matches Niharika. And 2, 1 doesn't match, but one of them is 1, right? All right. Don't think in terms of 2D only. When we graduate, for example, will the broadcasting be able to happen right here? Will I be able to broadcast?
Yes.
Yes. All right. 5, 5, 2, 1. Don't match, but one of them is 1. 4, 1. Don't match, but one of them is 1. We will be able to successfully broadcast this tensor for the arithmetic operations. All right.
Okay.
We'll see the failure scenario though. We have already seen some of the failure scenarios. We'll see more failure scenarios of broadcasting. Lohit, you had a question? Go ahead.
No, I didn't ask.
Okay. Now let's see how we get what do we get in the result? Again, let's go back to that intuition that what the user is trying to do and will the computer be able to imagine it? If we have a matrix over here of 1, 3 and a matrix over here is 2, 3, what will be the resultant matrix?
2, 3.
2, 3.
2,
So
3.
3, 3 over here, 3 and over here. Make sense? So we'll be able to have 2 from here and 3 from here, and we'll be able to get the resultant shape. If we have a tensor like this, 4, 1, 5, and 1, 3, 5. What will be the resultant? 5, 3, 4. That will be the resultant shape that I'll be having for the tensor. All right. Let's try it for if we have a matrix that is 1, 2, 3, that is 1, 3, and another matrix 1, 3, and another matrix that is 1, 2, and 3. This is 3 rows and 1 column. Make sense? 1, 3, and 3, 1. 1, 3, and 3, 1. What will be the result of this? 3 by 3. Make sense? I will be able to have 3 by 3. This will broadcast like this. These will broadcast like this. And we will be able to get the answer. Make sense? Let's try it. All right. A is 1, 2, and 3. And this one is 1, 2, 3. 1, 2, 3, 2. All right, we'll write the shapes and then we'll print the C. All right, 1, 3, 3, 1, and we'll be having a 3 by 3 matrix. Cool. So rather than going from the rules to how, just try to imagine that if we are giving these instructions, how will the computer try to behave? All right. Now let's try to do some of the tasks in the lab that we have to do it with the broadcasting. We'll do both the scenarios in which the broadcasting will be working, in scenario in which the broadcasting will be giving a scenario. And typically, in the interviews, the bugs or the issues that are happening, the interviewer wants to listen to this, that there is a shape mismatch bug. Because shape mismatch bugs lead to the broadcasting errors. All right. So a lot of bugs in machine learning are not algorithm-based bugs, not the model-based bugs, but they are the shape mismatch bugs. Because of the shape mismatch bugs, that you will not be able to broadcast the data. All right. They say that create an array A of, we'll be using the yesterday's random number generator and standard normal, a matrix of 1000 by 50. So I should be having a tuple of dimensions. And we'll be having a B, again a standard normal of just 50 dimensions, vector only. All right. If I want to do A plus B, I don't need to be reshaping them. No reshape required. I just need to do what? A plus B. Make sense? We'll be able to do A plus B. Now what we want to do is, here the broadcasting is happening. All right. Now what we want to do is, we want to take the norm of the rows. What does norm of the rows means? We talked a little bit about yesterday about the norm. What is a norm? Anybody?
You were saying some standard deviation.
No?
You were saying some standard deviation. No, I'm not sure.
That is normalization. All right.
Scalar.
Norm, not a scalar.
Magnitude, vector,
Magnitude of the vector. Magnitude of the vector. All right. Now, if I want to have a vector taking the physics student view on the right, makes sense? But when we will be writing the code, we'll be taking computer science student view. All right. So if we have a vector over here, which is 2, 3, which is basically Lohit's age is 2 years. Oh, sorry, his experience is 2 years. Experience is 2 years, and his, what do you call it? Experience is 2 years, and let's take age on. And age is 3 years. All right. So now what we want to do is we want to take the magnitude of this vector. How do we take the magnitude of this vector? There are two ways of taking the norm. L1 norm and L2 norm. All right. Basically length of this vector. All right. Two ways of taking the norm, that is L1 norm and L2 norm. This is also called Euclidean. And whenever we are talking in terms of machine learning, by default, we will be meaning L2 norm only, Euclidean norm only. If I want to take the distance of this, then I can do this just like coordinate geometry. Makes sense? Their distance from the origin. This is the way that we can take the norm. We can take the L2 norm. So L2 norm is Euclidean. L1 norm is not Euclidean. It is Manhattan. Manhattan. All right. In L1 norm, what we do is x1 minus 0, absolute, plus y1 minus 0, absolute. All right. So think of it like a distance in the blocks in US. All right. This distance, this distance. So now if we want to take the norm over here, we are talking about the Euclidean norm over here or the length of the vector. For example, in case of embeddings, all right, for example, if we have the model like this, age, revenue, plan, and years of experience, not revenue, salary, all right, and then some target that is churn, not churn. Make sense? So if we have age like this for Lohit, that is 32. What's your age? 32. Okay, salary, 300K, and experience as 4 years. All right. Now there is two kind of norms that will be happening in the tables. All right. One is the row norm, which is on axis. What is this axis?
Axis 1.
Axis 1. And what is this axis?
0.
0. All right. So there will be two kind of norms that we'll have to deal with in our machine learning. One is the row norm, basically taking the magnitude of this vector. It's called row norm, is also called vector norms. In case of embedding, where we'll be using AI, there we will be using the row normalizations, row norm like this. But in classical machine learning, we will be taking the norm, or we are going to do the normalization of the data according to the feature. All right. Just a glimpse of it. If the ages are 38, 39. If we are doing the analysis of the data, I'm just making a case or rationale for taking the feature norm or column-wise norm, that if you have 300K over here, 400K over here, 500K over here, all right, and 700K over here, 800K over here. Now this number is very, very big than that of age. If I just do the analysis just based on the numerical value of salary and age, this salary will offset, or it will be giving us much more weightage than that of age or number of years of experience, 4, 2, 3, 4, 8. So our model will not be correct. For example, if we are trying to find k nearest neighbors, then the salary scale will be dominating the whole model. Age and experience will not matter. That's why what we try to do is we want to normalize the data. We take the mean column-wise, we take the standard deviation, and we do the standardization of the data. That is called standardization, z-scaling of the data. We can do min-max norm also. There are different kind of ways that we can bring it towards the center, right? That's the rationale that we go feature-wise. We can do row norm also. In case of embeddings, I need to make this vector as a unit vector. There the row normalization happens. Make sense? So right now we are talking about row norm, that we have to do the normalization of the rows. All right. So in order to do that, what we are going to do is we'll use over here, we'll call a function that is safe norm. And you will come to know that why it is called safe norm also. Okay. Safe normalization of my which A. All right. So let's write a function, define a safe norm function on a matrix X. Sorry. And how do I take the safe normalization? That is norm is equal to np dot linear algebra dot norm of my X. Along which axis?
1.
1.
And keep dimensions equal to 2. All right. And then what we are going to return is np dot max maximum of n and 1e minus 2. Okay. Questions? Anybody any questions? Or everything is clear?
What are we trying to do?
Yes. So
I don't know.
did you understand x is equal to 1?
Yes.
Okay. Did you understand what np.linear_algebra.norm is trying to do? It is basically trying to do, it take the squares, the sum of the squares, and then takes a square.
Okay.
Okay. So it is just trying to do that if we have 32, 300, or rather than that, if we have 2 and 3 over here, it is just taking the square of them, adding them, and taking the square root. Make sense? It's exactly doing this. But keep dimensions is equal to true. I'm going to keep it fuzzy right now. That what is keep dimensions is equal to true. All right. So if we are calculating the norm over here for each row, and we are having 5 elements over here, how many norms I will be having for each? As for each row, I will be having one norm, right? Row-wise norm. I'll be having some value over here. Let's say 5. I'll be having 10, 11, 12. I'll be having 40. Make sense? So if I take a norm and I keep dimensions equal to true, what should be the data structure that I should be getting for the norm of the rows?
Vector.
A vector. Ideally, I will be getting a vector of 5, 10, 11, 12, 14, right? And the shape of that vector will be 5. Make sense? But with keep dimensions true, what we are doing is not taking a vector, we are getting a matrix. If I do keep dimensions, if I don't make the keep dimensions equal to true, I will be getting a vector over here. But if I do keep dimensions is equal to true, I will be getting a matrix. Make sense? Now, why is this? Why do we require a matrix? We'll see that. Now, if I do the A normalization, that is, we have to do the normalization of the A, then what should I do? How do I handle the arithmetic operation? Anybody? If I calculated the row norms, if I want to do the normalization of my matrix, the complete table that we have, what should I do? Ideally, huh? I just need to do A divided by norm of the rows, right? I just need to do this. We'll talk about this, that why did I take this? Don't worry about this yet. Just keep it at the back burner for now. But if I want to do the normalization of my data, my matrix, then I have to do A divided by the norm of the rows. Why? Because if I am, for example, in my use case, in the embeddings, remember I have to make this as a unit vector. If I want to make it a unit vector, then take the magnitude and divide. Magnitude is what? A distance. And divide that vector with the distance. I'll get just the direction. So the idea is that if we are doing a norm on the rows and we are dividing it, then we are just keeping the direction. And remember, for embeddings in the ChatGPT, we need just the direction. So for these kind of scenarios, what we are doing is A divided by row of norms. Now let's go to this thing that we created an A. We created an A which is of 1050. Make sense? An A was created which is 1050. When we took the norm of the rows without keeping dimensions equal to 2, Niharika is absolutely correct. We will get a vector. A vector of how many elements? 1000 rows, 50 features. So I'll get a norm of 1,000. I'll get a vector of 1,000. Now try to broadcast. If I try to broadcast it, what will happen? This moves to the right by the rules of broadcasting, and this will be 1. Will I be able to broadcast? I'll be getting a broadcasting error. And for the precise reason, what we are doing is keeping dimensions is equal to true. When we keep the dimensions is equal to true, it gives us a matrix of 1,001, not a vector. It gives us a matrix of 1,001. Now you can do the broadcasting. Now, if I do the broadcasting, I will be able to do the broadcasting. This is a matrix now, and I will be successfully able to divide these. I will be able to do the arithmetic operation on it. And that's the reason that we are keeping the dimensions equal to true. We'll see it in action. When we are keeping the dimensions equal to true, it will be working perfectly fine. But if I do keep dimensions is equal to not true, then I'll be getting an error of broadcast. Make sense? Let's try to code it out.
I had a doubt.
Yeah.
You just said that normalization according in classical machine. I missed that point. In classical machine learning, normalization always happens according to the feature.
Not always. I don't want to use the word always. Generally.
Okay.
Generally, it is a feature normalization that we will be doing.
So that is row wise.
That is column wise. Features, remember? Okay. So what is this? These are samples. Sample.
Okay.
Right? Or it is called, there is another name to it. You can call it rows or samples. Okay. And these are columns, or you call them feature, age feature, salary feature, experience feature.
Okay. But for vector embeddings, we do it row wise.
Yeah. All right.
Okay.
All right. For vector embeddings, one of the use cases I'm telling, I'm not saying that it cannot
be.
be.
We are doing it row wise now because we are doing it in vectors. Okay.
No. Not in the vectors. I'm just telling you what is the use case of the row wise norm.
Okay.
One of the use cases of row wise norm is embeddings. All right.
Okay.
Neither at a lot of machine learning in linear regression, the logistic regressions, or in the k-nearest neighbors, all right, all the supervised machine learning, at lot of places, or at most of the places, we'll be doing feature-wise normalization. All right.
It's like
and
a
one more.
convention.
Say that again. It's not a convention. It's not a convention. It's just, all right. I don't want to use a very strong word like convention. All right. At normal or general use case. General use case. All right. And you will be able to know that, okay, if I'm just doing this without standardizing this or without normalizing it, I will not be able to get this. But this is at a different scale. This is a different scale. So a typical way that the normalization is done is using standard scalar. For example, in scikit-learn, if you have used scikit-learn, standard scaling. All right. And one more thing, in machine learning, people use the things sometimes incorrectly. All right. For example, the scaling of the data, even though we are doing the standard scaling, that is z-scale normalization, we are doing the z-scaling of the data, it will be called normalization. All right. So experienced machine learning engineer will be using it. We are doing the normalization of the data. Its normalization is actually min-max normalization. All right. We are not doing the min-max normalization. We will be doing the z-scale or standard scaling of the feature, but they still will be calling it normalizing the data. All right. So be comfortable with that kind of fuzziness. They will be saying normalization of the data, but they will be doing the standard scaling of the feature. All right.
Okay.
All right. Where was I? Okay. Keep dimension is true is for this reason. Let's try to run this code. Then we'll come to this, that why did I do this? Okay. So if I try to run this, it works perfectly fine. But if I keep the dimensions not true, if I just go do it like this, I will be able to get a broadcasting error. All right. This is one of the use cases, Alok, where the broadcasting is getting used. everywhere broadcasting will be getting used in case of mathematical operations. All right. Now let's come to this. Why did I do this? This is a very important concept. That why did I take maximum? All right. Although it would have worked in some of the scenarios, it would have worked perfectly fine. But now we'll be going to a concept which is called numerical stability. Now, in computers are not humans. If you do 1 plus 2, then you expect 3. But a system can give you this sort. 1 plus 2 is equal to. It can give you this sort. Make sense? If you are specially doing very large numbers, and very small numbers, the compute can behave in an unexpected manner. And typically it is called tiny rounding of errors. Tiny rounding of errors can break your training of the data. If tiny rounding of errors can break your training of the data, then that is a situation of numerical instability. Whatever algorithm that we are writing, we'll be writing that, oh, I just need to take the norm. And somewhere you'll see that, okay, some extra term comes in. And that is a term which is basically we trying to make the norm as a safe norm, not a naive norm. Because if I am taking the square root, for example, if I take 2 square plus 3 square, or if it is very, very small numbers, right? 0.000000001 plus 0.000003 square. It will become even more smaller. If I add these very small numbers, then the numerical instability can happen on the negative side also and the positive side also. If it is positive side, very nice, fine, we'll be fine. What happens if it happens for the negative side? And we are taking a square root. That is a kind of scenario that we will be expecting our algorithm to work fine. But somehow it is failing. We don't come to know. We keep on looking at our model only. Is this correct? Is this logic correct? Logic is correct everywhere. The compute is backfiring. That is called the numerical instability. When we have very large number, very small numbers, when we have exponents, logs, inverse, in that kind of scenarios, again, the numerical instability can happen. In another scenario, when we have the repeated operations, when we have the repeated recursive, square. In those kind of scenarios, again, the numerical instability can happen. That's why, in order to save that, what we did was, whatever is the norm, if the norm is very, very small, then I'm taking, the norm is equal to 0, then remember I am doing A divided by rho norm. Anything divided by 0 is going to give me not a number. That's why I'm taking a very small positive value over here, very small positive value, so that at least I get some number. I don't get an error of not a number in my computer. Make sense? That's why I'm taking 1 e raised to minus 12. You can take very small other number also. It's fine. 1 e minus 5. Make sense? So this is for the purpose of numerical stability that we are taking a safe norm, not an ordinary. Anybody any questions till now? All right, let's move forward. Okay, pick the broadcasting trap. All right. So now it's a very common this situation. Okay, I just want to see what are the checks that we are doing. We are doing the checks on the shape. The shape of A should be 1050. It's basically just checking whether you have initiated the A correctly or not. B shape and broadcasting shape. All right. A plus B. Whether if we if we do the shape of A plus B over here, what should be the shape of A plus B? Print A plus B shape. Anybody? Remember, what is the shape of A? Is 1050 and this is 50 only. What should 1050 only? That is absolutely correct. 1050. Makes sense? And how will it happen? 1050 and a vector of 1000. Align it to the right. So this goes to the 1000 towards the right, and this becomes 1000.
That's 50.
Sorry.
That's 50.
That's 50.
That's 350.
That's 50. My bad. Sorry. This is 50. So this goes to the right. 1000, 1000, 50, 50, 50. So the shape of A plus B should be 1050, and that's what we are getting. That's what they are checking. All right. And what else they are checking? Row norm shape. What is the shape of the row norm? Row norm that we have calculated over here. All right. And that's why it is calculating whether you are keeping the dimensions true or not. You need a matrix to do this. Neither you'll be getting a broadcasting. All right. Those are the things that we discussed in the class. All right. Now we are looking at the broadcasting trap where it is going to fail. We pretty much know if I'm trying to broadcast a matrix with a vector. If I'm trying to broadcast a vector of 5 elements on a matrix of 3 by 4, will I be able to do it? It should be throwing us an error. Make sense? It should be throwing us an error that, okay, let me reset it. Okay. We should be getting a broadcast error raised for this. I should not be able to do it. They say, how do we fix it? I do fix it by A plus B, and fixed will be equal to np.ones of 4. All right. So rather than creating 5, I will be having 4. And that is the fixed shape. Shape is fixed now. We are not getting a shape error. And we'll be able to do the things correctly. Let me just see. Yep. All right. This is the way that we'll be fixing the shape. All right. Basically, the
We
idea
can also
is just,
do
yeah, you can do that. Yeah, I know what you're doing. We can do that. All right. We can do many things. All right. If you want, this is just to demonstrate that, okay, 3, 4, 5 will not work. All right. There are many ways that you can do it. All right. You can do this also. All right. This should also work. All right. Is that what you were trying to say? Yeah. Okay. So now let's go to this is as far as broadcasting is concerned. We are done with the broadcasting. Anybody, any questions till now? All right. So the next exercise that we should be doing is loop versus vectorized. We saw a little glimpse of it, but we'll be doing the exercise today. That how much is the difference between the loops and the vectorized operations? All right. So we'll create an array of 1 million. All right. So random number generator, standard normal of 1 million. Remember, for the readability, I can do it like this. Okay. And we are taking the initial time, and then we are taking the time after we have done. If we want to create an X loop, let's create an NP, empty like X. All right. I can initiate the array like this. Basically, it is creating an array of 1 million empty spots in which I will be having the data which is normalized. Normalized data is basically what we are doing is X minus mean divided by standard deviation. So in case of vectorized operation, I'll just throw it a matrix. In case of loop operations, I'll have to take each and every X1, X2, X3, I'll have to go over them, right? Same thing we are going to do over here, and we are going to see it, compare it with the vectorized operation that will be there. All right. Firstly, we create a X loop array, which is just like this thing. Then for I in range, that is length of or X dot shape 0. Shape 0 should be giving me the length of the, I have a tuple. I'll just get the zeroth index. That should be giving me what is the length. Huh? And then x loop I should be equal to, for each ith element minus xi, ith element in my I minus mean, let's call it mu, divided by standard deviation. I have not written the mu yet. Let me write the standard deviation. Let me write the mu. So if I want to calculate the mu, np dot mean of x. All right. I don't need to specify x is over here because it's a vector only. All right. I don't need to whether I have to take the mean or across the row or the column. Okay. And standard deviation also is np dot standard of my x. Okay. So either we'll do it like this, and then we'll note down the loop time, or in case of vectorized operation, all I need to do is x minus mu divided by. I'll come to your question, Lohit, just a moment. Divided by standard. All right. Standard deviation. Okay. We are just looking at the applications of NumPy. Okay. We are not going into the details of how do we do the statistics of mean or median or mode. We will go there when the next week the mathematics happens. Then we will be talking about them. This is just that okay, how NumPy is going to execute at a computer level. So we are taking a computer science student view right now. All right. If I do this, the loop time takes 0.32 times and vectorized time takes 0.003. We'll do one more thing. We'll just compare the speeds. How much x is the speed? So if we look at the speed x, then this is 159 times better than that of the loop, just on a small data of 1 million. Does it make sense? Lohit, you had a question? Go ahead.
Yeah, I was thinking like you're taking standard deviation, so mu and like standard deviation we already standard normal, so we already know mu and standard deviation. But then I realized it was just to check the time.
Yeah, it was just to check the time. It is not remember, when I will be doing the feature normalization, at that time I will be doing this, especially standard scaling. Make sense? And how do I do the standard scaling? Subtract the mean and divide it by standard deviation. Make sense? Basically, making a feature in the form of a bell-shaped curve where the mean is equal to 0. All right? That is what we intend to. Make sense? So that all the distribution of all these points, x samples, all these feature points should be around this mean. All right? That is what we are trying to do in a standard scaling. And yesterday we talked about what is Gaussian distribution, or z-scale distribution is mean is equal to 0 and standard deviation is equal to 1. 68, 95, 99 rule. Between 1 standard deviation, I will be having those points of the feature, 68% of the points. All right, 95% within the 2 standard deviation, 99% between 3 standard deviation. All right. And it is basically standardizing the data. Every feature is standard scale. Make sense? So that we are comparing apples with apples, not comparing apples with oranges. Basically, the idea is this. Common sense is this. All right? Okay. Now let's look at one more thing, that is pairwise distances. Now we are going to get into a little bit of linear algebra and then we'll stop today. All right. We are going to get into a little bit of linear algebra, but keep the focus rather than on linear algebra on the execution, that how NumPy is going to execute the things. If, for example, we will be doing k nearest neighbors algorithm. All right. We'll be building a model of k nearest neighbors, which will be a classification and a regression. Just going over there, I'm throwing out so many terms. Let me talk about what is regression. In machine learning, we'll be having generally 2 kinds of algorithms. Supervised and unsupervised we have already talked about, right? Among the supervised, we'll be further having bifurcation. What kind of algorithms I'll be having? Supervised is labeled data. We have the labeled data. One kind of algorithms models that I'll be having is regression-based model. Another one is classification. Examples of it is k nearest neighbor, decision trees, decision tree, random forest, gradient, XGBoost, gradient boost, SVM, k nearest neighbor. Many. In regression, we'll be having linear regression. But before going this, what is regression means? What is classification mean? This means numerical. A target is numeric. Target is numeric. Here, the target is analog, not continuous analog. 0, 1, true, false, low, medium, high categories. Make sense? So now, these are just, I wanted to clarify this, that you don't get alienated. Now, one of the use case is in the k nearest neighbors is we want to find the pairwise distances. If we have 3 elements over here, A1, B1, A2, B2, these are the points in the plane, A3, B3. We want to find the pairwise distances of A1, B, first point with the second point with the third point. And then second point with the first point, second point with the third point, second point with the second point itself, and third point with first point, third point with second point. So this is the initial matrix that I have. If I want to find the pairwise distances, how many elements I will be having? Fast, we have to go home also.
9 elements.
9 elements. And she's absolutely correct. 9 how? D1, distance of 1 from 1, distance of 1 from 2, distance of 1 from 3, distance of 2 from 1, distance of 2 from 2, distance of 2 from 3, distance of 3 from 1, distance of 3 from 2, and distance of 3 from 3. Can somebody tell me what will be these distances?
0.
Distance of a point from a point will be 0. All right. So these have to be 0. Remember that. Now, if we are talking about calculating the pairwise distances, can somebody tell me what will be D1? How can I represent D1?
B2 minus A.
A2 minus A1?
Mod of Euclidean, right?
Modulus of B2.
Square.
Exactly.
Square of under.
Again, coming back, if we want to take the distances, there are 2 kinds of distances. One is Manhattan, one is Euclidean. Manhattan is
A2
L1.
square.
Manhattan is L1 and Euclidean is L2. All right. So if I want to take the distance in the form of the coordinate geometry, if this is A1, B1, and this is A2, B2. All right, X1, X2, Y1, Y2. All we did was we can take the distance like this, A2 minus A1 square and B2 minus B1 square. This is L1 or Euclidean distance. All right. Another way of getting it is the way Lohit was saying. A2 minus A1 mod and B2 minus B1 mod. All right, that is Manhattan. And whenever we are talking the machine learning, by default choice is Euclidean actually. Make sense? And we'll come to know why it is Euclidean. The reason is, let me tell you one thing. Nobody will tell you. But Euclidean are much faster to calculate. They are much faster to calculate. In Manhattan, we can calculate it. It seems very rosy on the whiteboard. It seems very easy for the mathematics student. For the computer science student, this is hell. Because what happens? Broadcasting explosion happens. We'll see it when we go to the Manhattan. And Euclidean, we'll see that although we are calculating it between every element, See, remember, we said that we'll not be doing formula A11, A22, A11, A33. This with this. Imagine there is a 1 million by 1 million matrix. If I start doing it, m square, go home. But now what we are trying to do, we'll see the power of NumPy. That NumPy has to find the pairwise distances. It will not use this. It will do some magic. That's what we are trying to figure out. But for now, if we have to calculate this is the D12, A2 minus A1 square plus B2 minus B1 square root of. Correct? That's what we have to calculate. Now I'm going to modify it, or I'm going to calculate it on the whiteboard so that you start understanding what NumPy is trying to do. If I take this, then A1 square plus A2 square plus B1 square plus B2 square. All right. And minus of 2, I'm taking common. And this is
A2 minus A1 plus B2 minus A1.
A1,
A1, A2 plus B1,
B1,
B2.
A2 minus B. Plus.
Plus, you're taking minus 2 common, right?
Yeah. Plus B2 B. All right. So now focus just on this part. If I want to take this, then that is nothing but A1, B1, A2, B2. Now, this is not arithmetic multiplication. What is this term translates to? What does this term? Dot product.
Product.
A1, A2 plus B1, B2. Make sense? This translates to the dot product of this and this. So if I want to do this, then I can have A1, B1, A2, B2, and A3, B3. And I can have this as a transpose. That is A1, B1, A2, B2, A3, B3. All right. So if I take the transpose of this, then this gets converted into this. If I do this, now at D12 place, what will I be having? A11, A2, B3. This kind of, that will be stored right here. So this term, I'm writing it as that this is the initial matrix. Let's call it X. If I take X and dot product with X transpose, I'll get this. In English, what he's trying to say is that I do not need to do. If I take the dot product of the matrix with its transpose itself, which is super fast, I will be able to get this down. That's what computer science student came to know that, okay, if I expand it, if I try to rearrange the things, then I can take X into X transpose and I'll be able to find with this term right here. Now, this term right here, this term is what we have to find out. How do I find it out? It is nothing but A1, B1 and A2, B2. If I take the element y square and sum it up on x is 0. Make sense? If I take the element y square and sum it up 0, then I can get this term. A1 square plus B1 square. I can have A1 square, B1 square, right? I will have A1 square, B1 square, A2 square, B2 square, and A3 square, B3 square. If I take the square of the matrix, right? Just the square of the matrix. Just square each and every element. If I add it to the transpose of this A1 square, A2 square, A3 square, and b1 square, b2 square, b3 square. Make sense? If I add them together, no, not add them,
Multiply. No?
not multiply. Just a moment. Just a moment. This is 2 by 3 by 2. This is
2 by 3.
2 by 3. So broadcasting should not happen. I should be getting a broadcasting error. Just a moment. This term we know, x into dot product with x transpose. This is fine. This term we need. A1 square plus A2 square plus B1 square, or we'll do A1 square plus B1 square plus A2 square plus B2 square. If I multiply A1, B1, and A2, B2, A3, B3 with not a dot product, this is element-wise multiplication. Okay, A1, B1, and A2, B2, A3, B3. This is 3 by 2, and this is 3 by 2 also. Shapes match. All right. So if I multiply them, then A1 square, perfect. And then B1 square, A2 square with A2 square, and B2 square with B2 square. And then A3, B3, A3 square, and B3. Who was talking about the multiplication earlier? Who was asking about it?
Yeah, it's me.
What's your name, please? Yeah, Sushil.
Sushil.
All right. So 3 by 2, 3 by 2. We are able to broadcast. All right. Then we are doing the element-wise multiplication. A1 square, A1 with A1, B1 with B1, A2 with A2, B2 with B2. We get this. And A3 with B3, A3 with A3, B3 with B3. Make sense? This is element-wise multiplication. So broadcasting is still working over here.
Yeah, got it.
All right. So if I have this and we want this kind of scenario, then I can take a sum on the axis. If I take sum on the axis, then I will be reducing this to a A1 square plus B1 square and A2 square plus B2 square and A3 square plus B3 square. Now we are fine. All right. So the square matrix, if I take the sum across the axis 1, then I will be having A1 square plus B1 square, A2 square plus B2 square plus A3 square plus B3 square. This is the matrix, which is just element-wise multiplication with the broadcasting, with the power of broadcasting, super fast. All right, we'll be getting this square. If I take the transpose of this, A1 square plus B1 square and A2 square plus B2 square. This is the original square matrix only. A3 square plus B3 square. Add it to the transpose of this, A1 square plus B1 square, A2 square plus B2 square, and A3 square and B3 square. Again, with the power of broadcasting, this is 3 by 1. This is 1 by 3. What will be the resultant? 1, 3 and 3, 1. I will be having 3 by 3. 3, 3 matrix, right? So if I have 3 by 3, so at the first one, I will be having something, A1 square. I will be having A1 square plus B1 square plus A1 square plus B1 square. Don't worry about it. I want this one. At the second one, I will be having A1 square. So the matrix, resultant matrix, I'll be having something over here. Over here, I will be having A1 square plus B1 square plus A2 square plus B2 square. Make sense? So I will be able to get at this row, I will be able to get A1 square plus B1 square plus A2 square plus B2 square. And that's what we wanted. So what should I do? So firstly, just do the element-wise multiplication of x with x with x. Once that result is taken, let's call that as square matrix. Take the sum of it on the axis 1. Keep the dimensions true. Keep the dimensions true because I need 1, 3 and 3, 1. Make sense? So if I keep the dimensions true, and np dot sum across x is 1. Keep dimensions equal to 2. It will be giving me the square matrix. All I have to do is the square matrix with the broadcasting. I didn't need to do this with this with this. All I did is element-wise multiplication of this x with x itself, took the sum, and this will be square plus squares transpose minus of 2 into x dot product with x transpose. And we will be able to implement it with NumPy. We never had to actually go for each element, we had to go to each other element and calculate the things. Because if we had to calculate it, that would have been very, very compute heavy. And that's what we are able to reduce it with knowledge of linear algebra as a mathematics student and implementation of it using the NumPy. I'll be able to do this. That's how we will be calculating the pairwise distances without even making the pairs. Does it make sense? Let's see that in action. I'm going to quickly explain it, okay? All right. So we are taking a square matrix, multiply x by x, element-wise multiplication, not dot product. Different. Dot product is this. All right. Element-wise multiplication across the axis 1, taking the sum, keeping the dimensions equal to 2. Once we are taking the square matrix, then this distance between the two elements is nothing but square and square transpose that we have already seen over. Take the square matrix, take the transpose of the square matrix, and the third term is nothing but the original matrix x and transpose of it. Dot product. Here it is dot product. Here it is element-wise multiplication. Make sense? Once we have done that, the distance between the two elements, complete distance matrix. 3 by 3 distance matrix over here in case of whiteboard. In case right here, if we have 20 by 5, make sense? 20 sample and 5, 20 by 20. Matrix should be the return matrix over here, pairwise distances. All right. All I had to do is just element-wise multiplication, take the sum, take the square matrix, take the transpose of it, take the dot product of it, never go to the elements one by one. And we are able to fill the diagonal with zeros. Why? Because D11, D12, they have to be 0, 0. Naturally, they will be coming with 0, but remember, the issue is with the numerical stability. It may be possible that the distances that we are calculating, it may be possible that we don't have 0 exactly, we have 0.000001. I don't want to have 0.0001, so that's why I'm filling the diagonal with all the zeros forcibly. Guardrail. All right, additional guardrail that we have. All right, and in the end, all I'm just returning the square. Remember, we had to do the square, sum of the squares, and then in the end, take the square root. Make sense? That's how we will be calculating the pairwise distances without even going to the each and every element individually. Does it make sense? Yes, Ajay, go ahead. All right, and pairwise distances, the distance between 20 to 20, 20 by 20. All right, that should be the shape of my resultant matrix that we should be having, pairwise distance. This is just to show you that why NumPy will be doing some of the things. You will be thinking that I can do pairwise. But it doesn't do the pairwise one by one. Why? Because that will be compute heavy. We want to have the power of NumPy so that we can reduce the time. We can process our models much faster. All right. That's why we are using the power of linear algebra as well as the NumPy. Yes, Lohit, go ahead. What's your question?
So by default, can we assume that like by default NumPy is calculating Euclidean? Because
Where did I actually did the things, no? I did x
oh,
square. I did the
okay,
square root. All right.
okay, got it. Okay. I
All right.
thought like okay, then I didn't.
It's not, what I wanted to say that by default, if they say the pairwise distance, assume L2 distance is to be calculated.
Okay.
All right. But everywhere, even if it is libraries, then you should be giving a parameter whether you want to do L2 or L1.
Got it.
All right. So it's not that, okay, by default, it will be. We are actually doing it. We are taking x square. Makes sense? That's why I drive to this whole thing.
Correct.
All right. Anybody else, any other question? All right. Before going, sorry, I'll do one more thing. That is, I'll just quickly. Do we have time? Okay. Softmax regression. Logistic regression is a type of classification. Logistic regression, although the name is regression, but it is actually classification. Logistic regression is 0-1 classification. True, false, yes, no. All right. But if I have, what is softmax regression or multi-classification? Softmax regression or multi-classification is when we don't have two classes, when we have multiple classes. Revenue level low, revenue level high, revenue level medium, threat level low, threat level medium, threat level high. Color combination red, color combination green, color combination blue. We have multiple. In that scenario, we will be using softmax regression. Now, we'll not be going into the details of how we'll be implementing the softmax regression, but one of the activation functions for the softmax regression is going to be softmax. All right. Just for linear regression, what is the for logistic regression? Sorry, what is the function? What is the activation function that we use? It's called
sigmoid.
Sigmoid. Similarly, for multiple classification, we use softmax. We will be doing the derivations of the sigmoid function, that how do we derive the sigmoid function and how does it come. But for now, imagine that we do have the softmax. All right. And we have to calculate the activation function for a particular x. For a particular matrix x, we have to calculate. And how do we define the softmax function? We will be doing the derivation of it. But for now, I'm going to define it e raised to z over sigma of k is equal to 0 to n e raised to. All right. E raised to, let's call it cj. All right. So exponentials, sum of all the exponentials. For example, if I have 1000, 1001, 1002. All right. I have to take the probabilities. We'll go over there. For now, just understand that, okay, we have to use the probabilities. This is basically taking the sum of the probabilities of all the squares. All right, that is how that softmax will be representing. It will be representing the probabilities. When we go to the classifications, when we go to the models, at that time you'll understand. But what we need to do is e raised to 1000 plus e raised to 1001 and plus e raised to 1002 is what we have to calculate. In case of sigma, the denominator. If I'm doing the e raised to 1000, e raised to 1001, e raised to 1002, what is the possibility? What is the issue that can happen? Remember, in data structures and algorithm, we have the integer overflow. If we are doing e raised to something very big, what will happen? integer overflow. In this scenario, numerical instability. Remember, numerical instability happens when we have exponential e raised for something very big. In that scenario, we can have the numerical instability. In order to save the numerical instability, remember, this is the relative term, e raised per z divided by sigma of e raised per zj. So if it is a relative term, then what we are going to do is, rather than taking 1000, 1001, 1002, which can lead to numerical instability, what we are going to do is, we are going to subtract the 1000 from all of these elements. We'll normalize it. We'll take the maximum out of it and we'll subtract the maximum. I'm saying maximum, but I'm subtracting the minimum. I can subtract the minimum also because it is relative, right? I'll take the maximum between them and subtract the maximum. If I'm subtracting the maximum, this will become -2, -1, and 0. What it leads to is this time, e raised power -2, e raised power -1, e raised power 0 is much more manageable now. Not much more manageable, it is manageable. That's why when we are calculating the softmax function for this sigma, if we are doing this, rather than doing e raised power 1000, e raised power 1001, 1002, that is a naive way of doing the things. So we'll be calling it as a naive softmax, in which we are just taking the exponential and we are taking the exponential divided by exponential sum across x is 1, keeping dimensions equal to for broadcasting purpose. That is naive way of doing things. But what will happen is, if I do np dot exponential of x, e raised power 1000, e raised power 1001, e raised power 1002, that will lead to numerical instability. Instead of that, what we are going to do in a softmax stable softmax function, we are going to implement it that we are going to have x normalized by subtracting the maximum out of it. Why? Because this term is basically a relative term. It can be written exactly like this also. If it can be exactly written like this, NumPy will do this, and you will keep fumbling around. Why is it doing it? Because NumPy is trying to save the numerical instability that it can be right here, and it is just subtracting the maximum. Now it is much more manageable, and I'll be having the softmax stable in that scenario rather than naive way of implementing the softmax. Again, circles back to whether it is numerically stable or not. If it is not numerically stable, it will change the implementation under the hood like this. Don't worry, it is still this thing only. It is still implementing this thing only, but with the caveat of numerical stability. We are done with the class. Anybody has question can stay. Anybody who doesn't have question can leave. We'll continue from here. Probably we'll do the matrix multiplication and the. All right. Don't worry. Okay. Anybody any questions about today's session? Too many things to digest. We'll slowly digest them. We are just getting our feet wet with linear algebra. From the mathematics part will come next week. We'll be going into the details of the basics of linear algebra. Yes, go ahead, Ajay.
And I was just wondering, like, how are these concepts useful in terms of interviews?
They will be asking you, can you derive softmax?
No. So, will this be part of a larger?
There is a inherent assumption over there that I'll not be using this in the interviews.
Now, will this be part of a larger question wherein you have to identify these kind of caveats?
No, you will have to code, and if you are not doing the code with these things in mind, then then you'll keep wondering what is the problem which is happening. Make sense?
Gotcha.
All right, and you will not be understanding the under the hood things. It's as good as asking whether I should be knowing whether the array is a contiguous memory or not. You can do it without knowing it, but you will get stuck somewhere. For example, if somebody asks you, how does the indexing on array works? Can you do it without knowing that contiguous memory is there in the array?
No.
Can you say that, okay, why are we doing it like this under the hood in the library if we don't know the concept of numerical stability? Same reason.
Yes.
Yes, hello, go ahead.
They ask sometimes a question related to like softmax. why have you used this software function in this particular algorithm, and how to fine tune? Mostly logical related question behind the algorithm.
Anybody else?
Spinder, I had a question on broadcasting rules.
Mhm.
How would the rules break if we, let's say, take a four-dimensional data structure and compare it with, like, or do a addition with a two-dimensional matrix? I was not able to
Give
kind
me
of
an example.
visualize that.
Give me something which is troubling you in the four dimension.
Let's say 2, 3, 4, 5. The
Mm-hmm.
shape is 2, 3, 4, 5,
Mm-hmm.
and 2D shape is 3, 5.
T5. All right. So is this a matrix? This
Yes,
is
and it's
both are matrices. Not matrices. This is tensor. This is above tensor. 3, 5.
yeah,
Okay.
a higher dimension.
And you are thinking that I should be aligning everything to the right.
So in this case, 5 and yeah, I mean that's what I was trying to.
All right. 5, 5
5 and 5.
matches. 4
Yeah, but then there's
mismatch. Makes
yeah.
sense?
But what if it was 4 and 5?
Now we'll be able to do it. Now we'll be able to do it. Make sense?
Okay, yeah, makes sense.
All right. All right. Now we should be able to do it. I'll give you an example. Don't go over there. Stay at the tensor level. That if I have 2, 3, 5 and 3, 5. All right. All right. Or let me take 2, 2, 2 and 2 and 2. All right. Let me give you an example of the kind of matrix that it will look like. It looks like a 2 by 2 matrix. Two by 2 matrices. Huh? In this tensor, I will be having two 2 by 2 matrices. All right. So one is 1, 1, 1, 1. Another one is 1, 1, 1, 1. And another matrix that is 2 by 2. Let's call it 3, 3, 3, 3. Will I be able to broadcast? Very perfectly.
Yeah.
That's how you
Yes.
imagine. All right.
Yeah.
So that rules will scale. I never had seen it, right? I was able to look at the rules and I was able to derive an example. Make sense?
Yeah.
Better? All right. But here's another thing. All right. You, for the understanding purpose, you do it. But as a machine learning engineer, no, you should be thinking, because right now you're thinking 4 dimensions. Then you will be thinking 5 dimensions also. Then you will be thinking 6 dimensions also. Then you will be thinking 30 dimensions also. Now, if you have 30 dimensions, you can do the operations. But we'll see that from the tensor onwards, the broadcasting explosion starts happening. You should be thinking about the first thing. Do I need those many dimensions? Not, how do I process those many dimensions? Your mind will be, how do I process those many dimensions? If come what may, you'll have to do it. But the first thing that you should be asking is, can I reduce the dimensions?
Feature reduction.
Make sense? Can we do the dimensionality reduction? If I can do that, then that will lead to much more compute friendly operations rather than compute heavy. All right. That's a great question. All right. Anybody else? Any other question? Bye, guys. Have fun. I'm here only if you have any doubts.